Bearings are surfaces that support or are supported by other surfaces. A high-quality bearing needs to be composed of strong material capable of enduring pressure while allowing minimal friction and wear between surfaces. Precise positioning of parts is crucial for efficient and silent operation, enabling motion while minimizing friction in moving parts to prevent excessive power loss. Lubricated bearings of various types are utilized for this purpose, capable of managing radial loads, thrust loads, or a combination of both. Radial loads involve a rotating shaft held or contained in a fixed radial position, while thrust loads restrain axial movement along the shaft's axis. There are two primary ways bearing surfaces interact: sliding movement, sliding friction, and rolling movement, rolling friction. Generally, three types of bearings are commonly used: plain, roller, and ball bearings. These bearings are typically employed for crankshafts, cam rings, camshafts, connecting rods, and accessory drive shaft bearings. Although primarily subjected to radial loads, some plain bearings are designed to handle thrust loads as well. Materials used for plain bearings usually exclude iron and include metals like silver, bronze, aluminum, copper alloys, tin, or lead. Larger bearings, like those supporting various accessory section shafts, are known as bushings. Porous oil-like bushings impregnated with oil are widely utilized in these instances. During engine operation, friction heat brings oil to the bearing surface. Ball bearings. A ball bearing setup comprises grooved inner and outer races, sets of balls in some disassembling bearings, and a bearing retainer. These bearings are used in shaft and rocker arm bearings for certain reciprocating engines. Special deep groove ball bearings are employed in radial engines to transmit propeller thrust and radial loads to the engine nose section. Their ability to manage both radial and thrust loads makes them useful in gas turbine engines, supporting shaft ends to prevent axial movement. Roller bearings. Various types of roller bearings exist, but the ones commonly used in aircraft engines are straight roller and tapered roller bearings. Straight roller bearings handle radial loads only, while tapered roller bearings feature cone-shaped inner and outer race bearing surfaces, enduring both radial and thrust loads. Straight roller bearings find use in high-power reciprocating aircraft engines for crankshaft main bearings. In gas turbines, a rotating shaft is typically supported by a deep groove ball bearing, handling radial and thrust loads at one end, and a straight roller bearing, managing radial loads only at the other end. The enhanced brake horsepower from a high-power engine partly stems from increased crankshaft rotations per minute, RPM. Consequently, reduction gears are essential to regulate the propeller's rotation speed, ensuring efficient operation. When blade tip speed approaches the speed of sound, propeller efficiency drops significantly. Reduction gearing permits the engine to run at higher RPM, generating more power while slowing the propeller RPM, thus maintaining propeller efficiency. Gears for reduction gearing are typically machined from steel forgings due to the extreme stresses they must withstand. Various reduction gearing systems are employed, including spur planetary, bevel planetary, and spur and pinion systems. Spur planetary reduction gearing. This system involves a large sun gear attached to the crankshaft, a stationary bell gear, and small spur planetary pinion gears on a carrier ring. The ring is connected to the propeller shaft, and the planetary gears mesh with both the sun gear and the stationary bell gear. When the engine operates, the sun gear rotates, compelling the planetary gears to rotate as well. As they mesh with the stationary gear, they roll around it, rotating the propeller shaft in the same direction as the crankshaft, but at a reduced speed. Bevel planetary reduction gearing. Here, the driving gear has beveled external teeth attached to the crankshaft, meshing with bevel pinion gears in a cage fixed to the propeller shaft. The pinion gears rotate around the stationary gear secured to the front housing. A thrust ball bearing absorbs the thrust of the bevel pinion gears. This system is more compact than others, suitable for smaller propeller gear reductions. For higher-powered gas turbine turboprop engines, multiple stages of reduction gearing are employed due to their high output speeds. Lower-powered engines might utilize spur and pinion reduction gear arrangements for their specific requirements. Propeller shafts. Propeller shafts come in three primary types: tapered, splined, or flanged. Tapered shafts are identified by taper numbers, while splined and flanged shafts are recognized by SAE numbers. In low-power output engines, the propeller shaft is forged as part of the crankshaft, featuring a tapered design and a milled slot allowing the propeller hub to be keyed onto the shaft. The positioning of the keyway and key index aligns with the number 1 cylinder's top dead center. The shaft's end is threaded to accommodate the propeller retaining nut. Such tapered propeller shafts are commonly found in older and smaller engines. High-output radial engines typically feature splined propeller shafts. These shafts are threaded on one end for a propeller hub nut. Surrounding the shaft, a thrust bearing absorbs propeller thrust and transmits it to the nose section housing. The shaft also includes threads for attaching the thrust-bearing retaining nut. Between the sets of threads, splines are present to receive the splined propeller hub. Manufactured from steel alloy forging, the shaft extends from the housing and may connect to the engine crankshaft via reduction gearing. However, in smaller engines, the propeller shaft serves as a direct extension of the engine crankshaft, necessitating the engine crankshaft's rotation to turn the propeller shaft. In most modern reciprocating and turboprop engines, flanged propeller shafts are prevalent. These shafts have one end flanged with drilled holes to accommodate propeller mounting bolts. Some installations feature a shorter shaft with internal threading designed to accept a distributor valve used with a controllable propeller. Flanged propeller shafts are extensively utilized in the majority of propeller-driven aircraft configurations. The core principles governing engine operation revolve around the interplay between pressure, volume, and temperature of gases. An internal combustion engine is designed to transform heat energy into mechanical energy. This process involves vaporizing gasoline, mixing it with air, and introducing the resulting mixture into a cylinder where it gets compressed by a piston and ignited through an electric spark. The conversion of the ensuing heat energy into mechanical energy takes place within the cylinder. Figure offers a visual representation of the crucial engine components involved in this conversion and outlines the key terms used to describe engine operation. The operational cycle of an internal combustion reciprocating engine encompasses a sequence of actions: induction, compression, ignition, combustion leading to expansion of the fuel, air charge in the cylinder, and finally scavenging or exhaust of the combustion byproducts. Upon ignition of the compressed mixture, the resulting combustion gases swiftly expand, driving the piston away from the cylinder head. This downward piston movement, transmitted through the connecting rod to the crankshaft, is converted into a circular or rotary motion by the crankshaft. Simultaneously, a valve in the cylinder head opens to release the burned gases while the momentum from the crankshaft and propeller propels the piston back up the cylinder, preparing it for the subsequent stage of the cycle. Another valve in the cylinder head then opens to introduce a fresh fuel-air mixture. The valve allowing the escape of the exhaust gases is referred to as the exhaust valve, while the one permitting the entry of the fresh mixture is known as the intake valve. These valves are mechanized to open and close at precise timings by the valve operating mechanism. Consequently, the sequence of events in a four-stroke cycle engine unfolds as intake, compression, ignition, power, and exhaust. In engine terminology, the bore of a cylinder signifies its inner diameter, while the stroke denotes the distance the piston travels from one end of the cylinder to the other, specifically from top dead center, TDC, to bottom dead center, BDC, or vice versa. Operating cycles in the realm of aircraft engines span several types: four-stroke, two-stroke, rotary, diesel. The majority of certified aircraft reciprocating engines operate on the four-stroke cycle, commonly known as the Otto cycle, attributed to its originator, a German physicist. This engine type presents numerous advantages for aircraft use, particularly in accommodating high performance through supercharging. In this engine, 4 strokes are necessary to complete the cycle of events within each cylinder. It requires 2 full revolutions of the crankshaft, 720 derrick, for the 4 strokes, resulting in each cylinder firing once per every 2 crankshaft revolutions. The timing of ignition and valve events significantly varies among different engines due to multiple influencing factors. It is crucial to adhere to the manufacturer's recommendations regarding maintenance and overhaul in this regard. Valve and ignition event timings are specified in degrees of crankshaft travel. It's important to note that the specified timing marks the commencement of valve opening rather than the full open position. Intake stroke. During the intake stroke, the piston moves downward in the cylinder, decreasing pressure within the cylinder and allowing the air, metered with the correct amount of fuel by the carburetor, to flow through the intake valves into the cylinders. The intake valve opens before top dead center, TDC, on the exhaust stroke, aiding in drawing a greater fuel-air charge into the cylinder to enhance horsepower. However, limitations exist in how much the valve can be opened before TDC due to the potential for hot gases from the previous cycle to flash back into the intake system. High-power aircraft engines have both intake and exhaust valves off the valve seats at TDC during the intake stroke. Intake valve closure occurs about 50 dig to 75 dig past bottom dead center, BDC, on the compression stroke, ensuring better cylinder charging with incoming gases momentum. After the intake valve closes, the continued upward piston travel compresses the fuel-air mixture for optimal burning and expansion. Ignition typically occurs 20 dg to 35 dg before TDC to ensure complete combustion by the time the piston slightly surpasses TDC. Upon the piston's downward motion during the power stroke, the force from the burning gas's rapid expansion exerts immense pressure, up to 30,000 psi at maximum power output, converting the piston's linear movement into rotary motion through the crankshaft. Exhaust valve opening, usually before BDC on the power stroke, aids in effectively expelling exhaust gases, preventing overheating and ensuring thorough scavenging. Exhaust stroke. As the piston moves upward on the exhaust stroke, it expels the burned exhaust gases, creating low pressure in the cylinder, facilitating the inflow of the fresh fuel air charge through the intake valve opening timed from 8 degree to 55 degree before TDC. Revived in ultralight light sport and numerous experimental aircraft, the two-stroke cycle engine completes the operating cycle with just one upstroke and downstroke of the piston within one revolution of the crankshaft. Intake and exhaust functions occur in the same stroke. Featuring a three-sided rotor within an elliptical housing, the rotary cycle engine completes 3 cycles per revolution. It is utilized in experimental and light aircraft, known for its minimal vibration characteristics. Relying on high compression pressures to ignite the fuel-air charge, the diesel cycle involves compressing air in the cylinder, followed by fuel injection at maximum pressure, igniting and driving the piston. Diesel cycles operate on Jet A fuel, kerosene, and include various types like 2-stroke and 4-stroke diesel engines. Reciprocating engine power and efficiencies. Aircraft engines are evaluated based on their capacity to perform work and generate power. This section outlines the concept of work and power along with their respective calculations. It also delves into the efficiencies governing the power output of reciprocating engines. Work, according to physicists, is the product of force and distance. It's expressed as the force multiplied by the distance through which the force acts. Work W. Force, Fx distance d. Work W, force, Fx distance d. Work is quantified in several standards, with the most common unit being the foot-pound, FD/ETLB. If a 1-pound mass is raised by 1 foot, it represents 1 FTLB of work. The amount of work performed increases with higher mass and/or greater distance. Horsepower. Mechanical power is conventionally measured in horsepower, HP. James Watt, the inventor of the steam engine, discovered that an English workhorse could sustain 550 FTLB per second or 33,000 FTLB per minute for a reasonable duration. This observation led to the creation of the horsepower unit, the standard unit of mechanical power in the English system. The horsepower of an engine is calculated by dividing the power developed in FTLB per minute by 33,000, or the power in FTLB per second by 550. 1 HP FTLB per min 33,000 or FTLB per sec 550, 1 HP 33,000 FTLB per min or 550 FTLB per sec. Work occurs not just when lifting a force, it's exerted in any direction. For instance, dragging a 100 lb weight along the ground involves applying a force, albeit in a horizontal direction due to the ground's surface roughness. Imagine using a spring scale graduated in pounds to drag the 100 lb weight by pulling on the scale handle. Piston displacement. The greater an engine's piston displacement, the greater its potential maximum horsepower. Piston displacement refers to the volume displaced by a piston moving from bottom dead center, BDC, to top dead center, TDC. It's measured in cubic inches for many American-made engines and cubic centimeters for others. For a single cylinder, the piston displacement can be calculated by multiplying the cross-sectional area of the cylinder by the distance the piston moves in one stroke. In multi-cylinder engines, this product is then multiplied by the number of cylinders to get the total engine displacement. The volume V of a cylinder equals the base area, A multiplied by the height, H, expressed as V8AXH. The base area represents the cross-section of the cylinder. To find the area of a circle, the value of Pi is essential, representing the ratio of the circumference to the diameter of a circle. BP is approximately 3.4 accurate enough for most computations. The formula for the area of a circle is A equals PR2, where R is the radius, half the diameter of the circle. Radius R equals diameter D, 2. Total piston displacement for 14 cylinders. Total V8 VXN H 130 6712 in 3 X 14 H 1829 3968 in 3, rounded off to 1829 cubic inches. An alternate calculation method involves using the diameter of the piston directly instead of the radius in the area formula. Compression ratio. All internal combustion engines must compress the fuel-air mixture to derive substantial work from each power stroke. This compressed mixture resembles a coil spring, capable of delivering more work when compressed further. The compression ratio in an engine refers to the comparison between the cylinder's volume when the piston is at the bottom of the stroke to when it's at the top. It's expressed as a ratio, e.g. 7:1, reflecting the cylinder space difference at the two positions. Compression ratio significantly influences an engine's maximum horsepower, although its potential is curtailed by fuel grades, high engine speeds, and necessary manifold pressures for takeoff. For instance, a 140 cubic inch space at the bottom of the stroke compared to a 20 cubic inch space at the top results in a 7:1 compression ratio. Limitations on compression ratios, manifold pressure, and their interplay have a substantial impact on engine operation. Manifold pressure measured in inches of mercury, AEG, denotes the average absolute pressure of the air-fuel charge in the intake manifold. It's influenced by throttle setting, engine speed, and supercharging. A true supercharger increases charge weight, raising manifold pressure above atmospheric levels. This results in more charge forced into the cylinder volume, increasing horsepower output. Both compression ratio and manifold pressure determine cylinder pressure when valves are closed. Manifold pressure sets the charge pressure before compression, while the pressure before ignition is manifold pressure multiplied by the compression ratio. For instance, at 30 Hg manifold pressure and a 7:1 ratio, the pre-ignition pressure is around 210 Hg, while at 60 Hg it would reach 420 Hg. The compression event significantly influences manifold pressure variations, affecting the pressure just before ignition. If this pressure becomes too high, it leads to pre-ignition or detonation, causing overheating and potential engine damage. Pre-ignition involves the charge starting to burn before spark plug ignition, while detonation results in an explosive, uncontrolled burn that spikes cylinder temperatures and pressures rapidly. Engines with high compression ratios are used for long-range fuel economy, converting more heat energy into useful work compared to low compression engines. This leads to cooler engine operation and increased thermal efficiency. Manufacturers of high compression engines use high octane fuel and limit maximum manifold pressure to prevent detonation at high pressures while maintaining maximum horsepower demand and fuel economy. The indicated horsepower, IHP, of an engine is derived from the indicated mean effective pressure and other factors affecting power output. It's the power developed within combustion chambers without considering internal friction losses. To compute IHP, a mechanical indicator attached to the cylinder captures the actual pressure during the operating cycle, seen as a graph in Figure 01. The average pressure during this cycle, known as indicated mean effective pressure, IMEP, represents the constant pressure equivalent that would deliver the same work during the power stroke. The formula for calculating IHP for a 4-stroke cycle engine is represented as Planck 33,000, where P is IMEP in PSI, L is the stroke length in feet, A is the piston head area in square inches, N is the number of power strokes per minute, RPM, 2, and K is the number of cylinders. For instance, given values like IMEP, stroke length, bore, RPM, and the number of cylinders, the indicated horsepower can be calculated using this formula. The measurement of brake horsepower, BHP, involves calculating torque, expressed in pound-inches, lb/in, or pound-feet, lb/ft, which is the product of a force and its distance from the axis it acts upon. Devices like dynamometers or prony brakes can measure torque for engine output on a test stand. Torque calculation involves multiplying the force required to stop the motion of the arm by the arm's length. Once torque is known, the work done per revolution of the propeller shaft can be computed using the equation work per revolution 82px torque. The actual horsepower delivered to the propeller is known as brake horsepower, BHP. It is derived by subtracting the total horsepower lost in overcoming friction from the indicated horsepower. This difference accounts for friction horsepower, necessary to overcome mechanical losses such as piston pumping action and other moving parts friction. The equation to calculate bhp involves multiplying work per revolution by RPM and dividing the result by 33,000. This formula yields bhp as a measure of useful work delivered to the propeller shaft. The relationship between torque and RPM determines horsepower, showcasing that changes in either affect engine power output.